So in this last chapter, we got into equilibrium, and a reminder that equilibrium basically involves a certain type of reactions we've been talking about, which are these reversible reactions. And remember that these reversible reactions basically have these arrows heading in both directions. As we talked about, if the reaction is heading from reactants to products the way it's written, that is what is referred to as the forward direction of this reaction. And these reactions, because they are reversible, at some point, once you make some products, those products will decide that they would like to go in the opposite direction, heading back to the reactants. And that is what is known as the reverse direction here. And again, they will continue to pretty much do this until they reach what is known as equilibrium. And remember that as we talked about, when we talk about equilibrium, what we're talking about really is the rate. And we're talking about the rate of the forward direction will equal the rate of the reverse direction. So equilibrium doesn't mean that you have equal amounts of everybody on each side of the equation or anything like that. What it's referring to is that rate of the forward direction and the rate of the reverse direction will essentially equal each other. So basically, just as quick as you make products, those products will just as quickly break back apart into reactants. So ultimately what that does is it locks everybody into place in terms of either their concentration or their pressures, if you're doing something with pressures. Because they're going forward and reverse in the same sort of rate, they will be able to really maintain their concentrations and their pressures as well. And they will be able to maintain that really forever-ish, unless you do something to kind of screw it up, which we'll talk a little bit about today. But these type of reactions, as we talked about, although they may appear to be over with, when you're looking at, say, the beaker or something like that, maybe the reaction's over and it turned red or something like that. There is a lot of activity that's constantly occurring, is constantly going from reactants to products and back from products to reactants. And there is a relationship that we talked about here, which is known as the equilibrium constant. And remember that that is capital K. And ultimately, the way we calculate the equilibrium constant is we can take the concentration of our products divided by our reactants. And remember that we also need to take into account the coefficients that we see in the equations, the balance coefficients. So when we do that, we could go K is equal to the concentration of C. I would need to square it because of my coefficient here in this equation, times the concentration of D, which I would need to take to the fourth power because of the coefficient, divided by the concentration of A and the concentration of B. This would be, as we talked about last time, was sometimes also referred to more specifically as the Kc value, C meaning concentration. You would do all those sort of calculations there in molarity, moles per liter. And we also could, because these are all gases, now that I wrote G's next to all of them, we could also, as we talked about, do a Kp, where we don't look at concentration, but we look at pressures, and the partial pressure of C squared times the partial pressure of D to the fourth divided by the partial pressure of A and the partial pressure of B in this case. And that's what sometimes also referred to as the Kp value. Again, P meaning that you do it in pressure, and typically speaking, atmospheres is the pressure unit that you typically would use in this situation. The Kp and Kc values are typically just numbers. Any equilibrium constant is basically just a number. Although they are typically not the same value in most cases, they can in rare cases be the same number or numerical value, but in a lot of cases they are not. They will tell you the same sort of information as to what is going on in this reaction And again, if we have a large value of K, that means when we reach equilibrium, we would mainly expect to have products present. And that is because if we take a large number on top divided by a small number, we should end up with a large number. And if we have a K value that is small, that means when we reach equilibrium, we should mainly have reactants present. Same idea, larger number on the bottom, smaller number on top. It's going to give us a smaller number for K. Remember that the large value of K is 1 is considered a large value, or anything above 1 is considered a large value of K. And again, there is, as we talked about, sort of extremes to that. There's really, really large values like times 10 to the 54, and there's really small values like times 10 to the minus 34, and anywhere in between in terms of equilibrium constant type of values there are. Remember that the one and sort of only thing that can affect the actual value of the equilibrium constant is temperature. And remember that if you keep the temperature constant and you do a bunch of different sort of experiments doing the same reaction, so for example, like we talked about last time, maybe you did an experiment where you did all reactants to start with, or maybe you did an experiment where you did all products or a little bit of everybody. The equilibrium constant, as long as the temperature is the same in all those experiments, should come out to the same value. It should be constant for the way the reaction is written at that specific temperature. Again, I think I used like an example of like I want my equilibrium constant to be 2, and there's different ways that you could get there, like 4 divided by 2 is 2, 2 divided by 1 is 2, 8 divided by 4 is 2. So these are all different numbers, but proportion-wise, they basically all equal the same. And that's basically what will happen in these reactions is, even though you're starting with different amounts, in each case, the proportion or ratio of products to reactants will always be the same ratio, and you'll end up with the same value as long as you don't change the temperature. But again, a reminder that if we did K and did a bunch of reactions at 25 degrees Celsius versus the K value, say at 35 degrees Celsius, we would have different values between these two. But again, if you went to 35 degrees Celsius and you did all the experiments at 35 degrees Celsius, you should end up with the same value. But in comparison between 35 and 25, the value of K for that particular reaction will be different. And as we saw last time, we've already seen an equilibrium expression, which is that Kw that we use in the acid-base chapter. That is based off the equilibrium of water. And that is based off of this, basically, a reversible reaction that's occurring. Something else that we talked about is when we do write the expression for K, the only thing sort of included in that expression are things that are in the aqueous symbol or state, are the gas state. It's a really bad G. Gas state. Things we do not include in the equilibrium expression are things in the liquid state, are things in the solid state. So that's why when we write the equilibrium expression for this, we do not include the water, which is in the liquid state. So in this case, it's just the products that are involved. So anything that is a liquid or a solid is not included in the equilibrium. Again, a solid is basically just sitting there, not really participating in the equilibrium. And a liquid is a very constant concentration of it over time, and it doesn't really change like water. So it's not really changing all that much during this process. Any questions on any of that stuff that we just talked about the last time, I think? All right, so let us continue on here. So as we just talked about there, in a heterogeneous equilibrium, and that again just means that we have everybody in different states. We will not include solids or liquids. And so if we look at this, which is calcium fluoride, which is a solid, it will break apart into calcium ion and fluoride ions. And in terms of the equilibrium here, we will use our products over reactants. So here, just our product our F, and we do need to square it. Once again, this being a solid will not be included. So obviously as the one is boxed there, that would be the proper equilibrium expression in this particular case. Any questions on that one there? All right. All right, so let's talk a little bit about the next sort of idea of equilibrium, which is Le Chatelier's principle. And Le Chatelier's principle is the idea that you basically have a system that's at equilibrium. So you have this system that's at equilibrium. And frankly, you do something to it, you cause a stress, is sometimes referred to the system that's at equilibrium. What's going to happen in this case is you're going to mess up the equilibrium. So you'll no longer have a situation where the rate of the forward reaction, the rate of the reverse reaction will equal each other. And what happens though in these type of reactions are they will always try to get themselves back to the equilibrium state. So even though you go in there and you kind of screw it up, the reaction itself will sort of self-correct itself and try to get itself back to this equilibrium state. And there's really sort of three ways it can sort of happen. It can shift to the right. And basically what that means is you would need to make more products to do so, to get itself back to equilibrium. It could shift to the right, I'm sorry, to the left, which means you would make more reactants to get back to equilibrium. And there are certain situations that even though you did something to it, it really will not cause any change to occur, and sometimes referred to as a no change situation that will actually occur. So what happens in this situation is you do some type of stress, it causes the equilibrium to get messed up. The reaction will self-correct itself to get back to the rate of forward direction and reverse direction equal each other. And it will once again get back to equilibrium. And you can kind of mess around with it a lot. You can mess up the equilibrium, come back. You can mess it up, go the other way. You can actually force the reaction to go left or right based on the way it's written. And by the way, when we talk about left or right or shifting left or right, clearly everything's in the beaker together, right? So we got a little bit of reactants, you got a little bit of products, or it's in the container if you're dealing with gases. They're all in there together. So there really is no right or left in terms of the beaker or anything like that. So when we talk about right or left, we're talking about the actual equation that's written, and we have our reactants going to products. So for example, if something shifts to the right, then we would be going towards the product side. Something shifts to the left, we would go towards the reactant side. That also includes, like, for example, if you added something, that's a reactant, or if you added something as a product, we think about it as adding something to the left side of the arrow or the right-hand side of the equation in this particular case. What are the stresses that you can do to a system that's at equilibrium? You could do something with the concentration. So that is one thing that you can sort of do. You could also do something with the pressure and volume if it is a gas involved or gas sort of equilibrium. You could also do something with temperature as another sort of stress. And you could also do something like add a catalyst, which we'll talk about a little bit later on. So these are all different things that you could do to a system that's at equilibrium. And again, like I said, it will mess up the equilibrium, but the reaction itself will adjust in such a way to get itself back to equilibrium. So we're going to talk about each of these individually and what happens along the way as we do something with them. So we're going to start with concentration first off. Excuse me. There's really two things you could do. You can either add more, and when you add more concentration, the result of that is it will always shift away from the side you added it to. So add away is what happens. So if you add some reactants, it will shift away and go to the products side. If you add products, it will shift away and go to the opposite side, which is the reactant side. The other thing you could do is remove. And when we remove something, it will shift towards the side you removed. Now, when we add something, that's pretty simple. You can just pick up a reagent bottle and maybe iron's involved. So maybe you grab something like iron 3 nitrate and you drop it into your beaker. That's basically a source of iron. So you can just simply add it in. So if there's something in the equation that you look at and you have some type of source of it, maybe there's silver, you can grab some silver nitrate and you dump that in there. Maybe there's chloride, you can grab some sodium chloride and dump it in there. So if there's something that's available on a reagent that you could add as a source of something, you could put it in there and that'd be like adding. Removing is a little bit different. For example, if I had some chloride ions floating around in the solution and I wanted to remove those, I can't just reach in there and grab out the ions, probably not recommended, right? So in this particular case, chloride wouldn't be in my equilibrium, or chloride is in my equilibrium, but I could add something to it like, say, silver nitrate, and silver nitrate really is a source of silver ions and also nitrate ions. But silver and chloride, based on solubility rules, means they're going to make a precipitate, and that's going to precipitate out basically all the chloride that's in that solution. And that's essentially like reaching in there and grabbing it out, because now that chloride is no longer aqueous, it's now a solid, which is not part of the equilibrium, and that would be like you removed it. So that's a very easy way to sort of reach into like a solution and remove some ions, is you add something that's not in the equilibrium reaction, but that will react with somebody and make a solid. Another way that this sort of happens, again, you can make a precipitate. That's obviously something you can a lot of times see. If you had a beaker that had hydroxide in it, or maybe even had a beaker that has some H plus in it, you could add some base here to this beaker. And when you add base, you're adding hydroxide. Hydroxide and H plus will make water, which is liquid and not included in the equilibrium. So that would be in that case like removing H plus from that solution. You could also add a acid over here to this guy. That's like adding H plus, which would also react with the OH minus and make water. So if you happen to have an equilibrium that has hydroxide in it, or you have an equilibrium that has H plus in it, you could add either an acid or base to it. You could actually make water, which once again is not included in the equilibrium and would be essentially like removing those guys. Visually, you might not actually see that you made water, but unless you have something else in there that will change color as a result of that happening. But that's a one way you could remove that. So how this really works, if you just kind of take, we have like a reactant side, we have a product side, and we have this system here at equilibrium. Nice stick figure drawing here. So this guy's at equilibrium in this case. So in this case, if we added more products, and if somebody jumped onto this side, this is what's going to happen in this case, right? And we obviously now have messed up the equilibrium in this case. So to fix this, right, we don't need more people on the right, but we actually need more people on the left to fix this. It's going to shift away from the side we added it to. And now this thing is going to come back into equilibrium here. And we're back to equilibrium, basically number 2 at that point. So when we add, it really goes away. Why does it really go away? Well, for example, in this particular case, we added more products. When we add more products, if we think about our reaction, we have products on the right-hand side and reactants on the left. When we add more products, that's going to allow more products to be available. and that's going to actually kick off the reverse reaction to occur. So it's going to actually cause the reverse reaction to occur because of the availability of products being there, and that's going to cause us to head towards the reactant side. Now, if we did the same thing over here with our removal situation, so we start out here at equilibrium. Everybody's sort of happy here. And then this guy decides he's just going to hop off. So this guy decides to hop off. You end up with this situation here. Not so good. Again, to fix this, we actually need more people over here where the guy hopped off. We actually have to go towards the side that we removed it from. And that's going to get us back into equilibrium in this case. So you could think of it as when you remove something, you could think of it as like you created a hole on that side and you got to fill the hole. So things will go towards the hole to fill. What's really happening in this case is actually the opposite effect. When I remove my products, I actually end up in this situation with more reactants now than products. And because I ended up with more reactants than products, that's going to cause the forward direction to occur. And that's why it actually shifts to the right in this particular case. So really when you do something to an equilibrium reaction, what's really happening is either you're going to initiate the forward direction of that reaction to occur, or you're going to have the reverse direction of that reaction to occur. And again, so when we add, it goes away because of that. And when we remove, it goes towards it. Any questions on that there? The other situation that you could have is something that involves pressure and volume. They usually are sort of tied together. So what is the deal with this? If you remember Boyle's law, as the pressure goes up, volume goes down, and vice versa. As the pressure goes down, the volume goes up. And in this situation, if you have an equilibrium that involves gases, you can look at the pressure or the volume, and they both basically kind of work the same way. If the pressure goes up, which is the change that's occurring, that's because the volume goes down. So essentially what we have now is a small volume, and obviously the pressure is going up because everybody's in a very small volume. That's going to lead to a lot more collisions occurring, and that's why we see the pressure start to rise. We want to kind of fix that by bringing the pressure back down. So because the volume now is small, we actually will need less gas molecules in that situation, and it would shift to the side with the least gas molecules. Now that is obviously dependent on the reaction you're looking at. How can you determine how many gas molecules everybody has? You basically go to the equation, everybody with a G, you add up the coefficients on each side, and whichever side has the most is more, and whichever side has the least is the least. The opposite here, if the pressure goes down, our volume went up, so now we have a much larger volume, and that's going to take longer for everybody to collide with each other if they're gas molecules. That's going to start to see our pressure decrease. To fix that, we want to bring the pressure back up. So it would shift to the side with the most gas molecules. And again, that is dependent on the equation that you're looking at. Any questions on that there? So let's take a look at one here. Let's just say we had 3A plus B goes to C plus 5D in this case, right? So what's going to happen in this case? Will it shift to the left, shift to the right, or no change? If I do the following things, I add some C, I remove A, I increase the pressure, I add D, I remove B, I add A and I increase the volume. So for each of those things, which way should the equilibrium shift here? In this case, we're going to add C. So C is over here on the right-hand side of the equation. And when we add, it does go away from it. So it should shift the equilibrium to the left in this case. Again, the reason for that is when we add C, we now have more products and reactants, and that's going to kick off the reverse reaction, which is why it's going in that direction. When we remove A is over here on our reactant side. That again makes kind of like a hole over there on the reactant side that needs to be filled, and it will go towards the side we removed it. The reason for that is really the same reason. When we remove A, we now again have more products than reactants, and that's going to cause the reverse reaction to occur. We increased the pressure, which means the volume went down. And remember, volume is kind of what you want to look at. Small volume means less gas molecules is needed. That will bring the pressure back down. In this case here, there are a grand total of 4 gas molecules, 1 there and 3 there. On this side, there is 1 gas there and 5. That is 6 gas molecules. So in this particular case, it will actually shift to the left, which has the least number of gas molecules. Any questions on those 3 there? Taking a look at the next one, we're adding D. D is a product. That means we're going to have more products than reactants. Going to cause the equilibrium to shift away from it, which would mean to the left. Here we're removing B, causing a hole over there on the left-hand side. That's going to cause the equilibrium to shift that way. Once again, we're going to have more products than reactants. Adding A will actually give us more reactants than products, causing the forward direction to occur and shifting away from the side we added it to. And lastly, increasing the volume, that's going to decrease the pressure. Larger volume means I need more gas molecules to fix that. So it's going to go to the right. Any questions on any of those? So again, as I mentioned, ultimately what you're doing is either kind of increasing reactants or products and decreasing either reactants or products. So whichever one gets more of, or you have more of, that will cause either the forward or the reverse direction basically to occur. Any questions on that one there? All right, the next major thing we can do with this is temperature. And temperature works the same way as concentration. So it works the same as concentration, which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So how do you know sort of which way is temperature in the equation? It has to do with the type of reaction you're dealing with. If you're dealing with an exothermic reaction, heat and energy is being released. So when we think of an exothermic reaction, we think of heat and energy as being a product. So if you increase the temperature of an exothermic reaction, it should shift away from the right-hand side and go to the left. If you decrease the temperature, put everybody on ice, it should actually come towards the right-hand side or the product side. And that is different than in an endothermic reaction. In an endothermic reaction, heat is absorbed. And in that case, what we think of as heat and energy as a reactant rather than a product. So if you increase the temperature of an endothermic reaction, it'll go to the product side. If you decrease the temperature of an endothermic reaction, it'll go to the reactant side or go towards it in this case. remember that probably the most common way that you'll be told in chemistry if a reaction is sort of exothermic or endothermic is they oftentimes will give you your delta H value, your change in enthalpy, as we talked about in the energy chapter and a couple other places. And if it is a negative number, that usually implies that the reaction is exothermic. And if it is a positive number, it is endothermic. So it doesn't really matter, for example, the number in this case, it's really the sign that's important, as we talked about. Pretty much energy, any way that you calculate it, if you have a negative value for energy, usually implies an exothermic process occurring, while a positive one implies an endothermic process. Any questions on that one there? Lastly here, you can have something like a catalyst that you add. A reminder, as we saw earlier, a catalyst is not a reactant. It's not a product. It does not get used up in the reaction. It is there, as we talked about, to basically facilitate the reaction happening more efficiently by lowering that activation energy. So in the case of this, it will actually cause a no change to occur. Just get you there quicker, basically, but it will cause a no change. And that is an option in these sort of questions. This is probably the most common way that you could get a no change. Another way that you could actually get a no change is what we saw here. When you're counting up your gas molecules, you may not have any difference. So if you had this, which was a gas, plus this, which was a gas, then it goes to this, which is a gas as well. That is 3 gas molecules here and 3 gas molecules here. There is no side that's more or less. It's basically a tie in this case. In this case, you would get a no change. The other way that you sometimes could also get kind of a no change is sometimes like you add like a noble gas, like helium or something like that. Noble gases, right, group 8 are chemically inert, so they really won't react with anything, and that's another way. So those are 3 sort of common ways you could kind of get a no change in a Le Chatelier's principle sort of question. Any questions on that there? So let's take a look at one here. Let's just say we had this plus this makes this. And we'll go delta H is probably nowhere near this number. We'll go positive 130 kilojoules. All right, so same idea here. What's going to happen in each of these cases? Will it shift again to the left, to the right, or no change? If we add NH3, we increase the pressure, we decrease the temperature, we increase the volume, we add some H2, we remove N2, we increase the temperature, we add a catalyst, and for good measure, why don't we remove NH3? All right, so for each of these, which way are we shifting? And when we add, it does go away from the side we added it to. We added it to the right. It's going to cause it to shift to the left away from it. Again, it's going to add more products and cause that reverse reaction to occur. Increasing our pressure, decreasing our volume. So we're looking for least number of gas molecules. This side's got 4. This side has got 2 gas molecules. So it will shift to the right in this case. If we decrease the temperature, in this case, this is an endothermic reaction, as we see a positive number here. That means heat would be considered a reactant. So in this case, we're going to be removing a reactant, which is going to create a hole on the reactant side and cause the equilibrium to shift towards that side in this particular case. If we increase the volume, that means we actually need more gas molecules. That would also cause it to shift to the left. Again, that's going to cause our pressure to go down. So to bring our pressure back up, we would need more gas molecules there to cause more collisions. Adding H2, H2 is over here on the left-hand side. Since we're adding, it will go away. And again, it's going to go away because we now have more reactants than products, and that's going to cause the forward direction of this reaction to occur. Removing N2, which is a reactant, that's going to cause a hole on the reactant side that needs to be filled. So we will go towards the reactant side. Increasing the temperature, since it's an endothermic reaction, that's increasing our reactants, causing the forward direction to occur, and it will go to the right-hand side. A catalyst here will cause no change to occur. And lastly here, removing NH3, which is a product, causing a hole on the product side, going to cause it to shift towards it. Really, again, because we now have more reactants than products in this case, and that's going to cause the forward direction to occur. Any questions on any of those there? All right. All right, so as we've been talking about, effect on concentration, add away, remove goes towards. Volume and pressure, again, are usually tied together. Like I said before, I usually like to think of it in terms of volume. I know if I have a small volume, I need less gas molecules, so those go together, small, less. And if I have a larger volume, I need more gas molecules, so big volume, more gas molecules, small volume, less gas molecules. And obviously temperature works the same way. And as we've talked about previously there, again, temperature really is the only thing that changes the actual value of it. And it determines whether or not it's exothermic or endothermic. You could also use that knowledge to help you make a prediction about what will happen to the equilibrium constant value if you did something. So for example, let's just say we had our reaction there we were just looking at, which was endothermic. So heat is over here. And let's just say at 25 degrees, the K value is 50. Right? Now, if I raise the temperature here to say 45 degrees Celsius, would my K value be more or less than 50 in this case? Well, let's start with what will happen if I raise the temperature. Will it shift to the left? Will it shift to the right? Will it stay the same? In this case, it should. If I raise the temperature here, that would be like adding more reactants. Should cause it to shift away. That means that I actually will be making more products in this case, which means when I calculate my equilibrium constant at this higher temperature, my products are actually going to be a larger number than my reactants, and that's going to result in my K value actually being higher than 50. We'll go 60, for example. It's going to be higher in that case because I increase the temperature. Now, if I lower the temperature to like 15 degrees Celsius, that is less, which means I'm removing this. That's going to cause the equilibrium then to shift to the left, which means in this case, I actually will have more reactants than products. And that's going to cause me to have a smaller K value than 50, maybe 25, for example, here, or 26, just not use the 25 number there. So it's going to be a smaller K value. So if you know if a reaction is endothermic or exothermic, you can make a prediction, for example, what will actually happen to the equilibrium constant value if you raise the temperature or lower the temperature in this particular case because of the shift that's going to occur. Again, if I was to keep it at 45 degrees and do a bunch of experiments, I should hit 60 pretty much in my example here for my equilibrium constant. If I left it at 25 degrees, I should hit 50. And if I left the reaction at 15 degrees, I should end up with a K value of 26 in my example. Again, the comparison of changing the K values from different temperatures, we will get different K values again, but you will get consistent K values at a consistent temperature. Any questions on that there? All right, so let's take a look at this one. Consider the following reaction. how many of the following would lead to a shift to the reactant side? So let's go through this and see. If we remove CO, again, in this case, CO is a product. We're going to remove it, and that's going to create a hole on the right-hand side that needs to be filled, so it should shift to the right. So that is definitely not going to increase our reactants, right? That's going to actually increase our products in this case. Again, in this case, we have more reactants than products, so it's going to head to the right. If we add O2, O2 is a product, that's going to actually increase our products and cause this equilibrium to shift away from the side we added it to and actually go to our reactant side. So that would definitely increase the reactants. If we added, or sorry, if we removed CO2, removing CO2 will cause us to once again have more products. More products will cause the reverse reaction to occur, and it will go towards our reactant side, so that will also do it. And if I increase the pressure here by decreasing the volume, my volume went down, my pressure went up. This is 2 gas molecules. This is 3 gas molecules. So remember, small volume, small gas molecules, that should cause the equilibrium to shift to the left. So it's basically these 3 things here will all cause the equilibrium basically to shift to the left. The first guy will cause the equilibrium to shift to the right. Any questions on that one there? Taking a look at this one, which is an endothermic reaction, we want to know how many of these will cause H2 to decrease. So let's see. If we add water, H2O, it is a reactant. By the way, this water counts because the phase of this water is gas, not a liquid, and gas does affect the equilibrium. So by doing that, we're adding water. That means it should shift away from it and head towards the product side. So that is going to increase the amount of H2, right? Because we're going to make more products. The volume of the container is doubled, so my volume goes up. That means I need more gas molecules to fill that larger volume. And in this case, we have 2 gas molecules there. And here we have 4 gas molecules. That is also going to cause the equilibrium to shift to the right. That once again will not decrease my H2, it's actually going to increase my H2. CH4 is removed. CH4 is a reactant. That's going to cause us to have more products than reactants. It's going to shift towards the side where we made a hole to fill it, and that will actually go to the left. That right there is the one thing that will decrease the amount of H2 because it's going to the left-hand side. Lastly, the temperature is increased. Because this is endothermic, heat will be a reactant. And if we increase it, it's like adding more reactants, going to cause it to shift away in this case. So it's actually number 3 here that will cause that decrease in H2. Any questions on any of those, or Le Chatelier's principle in general? Yeah. Okay. All right. All right, so we talked about obviously large value K means we mainly have products. Small value, obviously, we have reactants. And obviously we'd go to the right or left. So let's talk a little bit about, again, a couple of things here in terms of equilibrium. If we are given the equilibrium concentrations like we are here, we could use our expression to solve for something that's missing. So in this particular case here, our equilibrium expression would be HI, and we would square it, divided by H2 and I2, which are reactants. That would equal 50. In this case, they gave us the concentration at equilibrium of HI, which is 5 times 10 to the minus 1, again squaring it, divided by our H2, which is what we're looking for, and our I2, which is 1.5 times 10 to the minus 2. And that equals 50 in this particular case. And here we're going to basically exchange these two. And that will end up with like what we got on the bottom there, our 5 times 10 to the minus 1. divided by 50 and divided by our 1.5 times 10 to the minus 2 is equal to our H2. And it does equal this guy right there. So remember that you can only use equilibrium concentrations to go into an equilibrium constant. And if they are not, you actually have to do a little calculation to figure out the equilibrium concentrations, which we'll talk about right now, actually. So let's talk about this calculation that if you're not given the equilibrium concentrations, what you would need to do. And again, you really won't see any of this here until you get to 1B. So I don't know why they teach it in this class, but we'll talk over just a little bit about it, just in case we do. So when you're solving equilibrium problems, there is a certain type of calculation that we use to actually do them. And this was referred to as ICE tables. And ICE tables, the I stands for initial. The C stands for change. And the E stands for equilibrium. And in this particular case, you would typically be given initial concentrations of something. So let's just take A plus B goes to 2AB. And if we write the equilibrium expression for this is AB squared divided by A and B, and we'll just make up a number like 10 it equals in this particular case. So let's just say initially we had 4 molar of A, and for B we had 4 molar. And we wanted to know what everybody's equilibrium concentrations were. So to do this, we would initially start with 4 molar and 4 molar here. And in this particular case, if they don't mention anything about the product, we can safely assume that it's 0. So if they don't mention anything about the product, then you can safely assume it's 0. The change part is represented by the letter X. And we use X to represent basically the change that's occurring. And in this case, we do have to actually take into account the coefficients here. And the coefficients are our stoichiometry, our mole-to-mole relationship. And if you don't take into account the coefficients, you will get the calculation wrong. You could actually do limiting reagent type calculations, this method here. Now, for example, because we have no products, the only choice for this reaction is the forward direction has to happen. And because the forward direction is happening, that means that the amount of reactant should be decreasing with time and the amount of product should be increasing. And we represent that with minuses and pluses. So this would be minus x, and it's really minus 1x because the coefficient there is 1. This would be minus 1x because it should be decreasing with time and the coefficient is 1. The product should be increasing, so this would be plus 2x here, again because the coefficient there is 2. If we take this down to our equilibrium, this is 4 minus x, 4 minus x, and 2x in this particular case. First off, any questions on that table? The C part is really the important part. Again, using those coefficients. If you don't have them, then you're obviously not going to get your mole-to-mole relationship correctly. What we do at this point is it really becomes just a math problem, and the goal here is to solve for x. So to do this, we actually will put everything into our expression. So that would give us 2x squared divided by 4 minus x and 4 minus x, and that equals my 10. Now at this point, if you happen to come across a problem in this class, my guess is it's going to be a perfect square, just like it is here. You could actually take a big old square root on both sides and you'll be in business. Now, when you get to 1B, you probably won't always get a nice easy one like that. You'll actually have to do something like quadratic formulas and successive approximation, depending on the bad teacher you might have, who knows. But you could do some assumptions as well. But for here, it'd probably be a pretty straightforward one here where you would just square root both sides. If we do that, that's going to give us 2x on top. It's going to give us 4 minus x. And the thing I usually forget to do, which is actually take the square root of 10. So we'll do the square root of 10 here. And that's going to be 3.1623. We then can multiply this to the other side to try to help us solve for x. So that'll give us 2x is equal to our 3.16 times 4. Can give us 12.649 minus 3.1623x. Again, we're just multiplying that whole bottom term over to the other side. We want to combine our x's, so I'm going to add this guy to the other side, and that would get me 5.1623x equals 12.649. We're going to divide it out. So I divide my 12 and change by 5.1623. Going to give us a 2.45 as our x value. So in this particular case, that is the x value that we see all through our table here. And that's going to allow us to get to the concentrations that everybody at equilibrium. So if we wanted to get the concentration of A at equilibrium, it equals 4 minus x, which means 4 minus 2.45. And this is molar here, so 4 minus 2.45, 1.55 molar. If we wanted to do B at equilibrium, we could look at the table, and it is 4 minus x here. So that's going to give us the same thing, 4 minus x, 4 minus 2.45. Going to be 1.55 molar. And if we wanted AB at equilibrium, it equals 2x. So the concentration of AB at equilibrium is 2 times x. That's going to be 2 times 2.45. And that would get us 4.90 here. And these would be the equilibrium concentrations of everybody once this reaction reaches equilibrium. So what do we see here? We see that what we expect to happen, we started with 4 molar of our reactants. At the end of the reaction, once it reaches equilibrium, they both have 1.55. Their concentration went down because they were needed to make products. The products, we started with nothing and ended with 4.9. So we increased our products, which is what we also would expect. This is also math, which means that, you can check yourself to make sure you didn't screw up the math, because now that I have the equilibrium concentrations, I could actually put it right into this expression, and I should end up with 10. And if I do that, if I take my 4.9 and square it, divided by my 1.55 times my 1.55, I basically get 10. And that's a good way to check yourself, especially if you remember when you get to 1B. It's a good way to check yourself because it can get a lot more complicated in terms of the math part of it. So it's a good way to check you didn't screw up the math too much. If you put it back in there and you got like a equilibrium constant of like 400, you definitely screwed up the math somewhere along the way there. Any questions on that there? Okay. So one last sort of equilibrium that, again, not really sure why they talk about it here, but we'll just mention it is KSP. KSP is an equilibrium, and it's actually for things that are insoluble. So it is for things that are typically insoluble based on solubility rules, like our silver chloride. Our silver chloride, based on solubility rules, is insoluble, which means that you would expect a solid to form. But even things based on solubility rules that are said to be insoluble will still break apart a little bit and will set up an equilibrium. And all these KSP ones are like this. We have solid on the left-hand side of the arrow, and aqueous ions on the right-hand side of the arrow. And we can write a KSP for this, which would be the concentration of silver times the concentration of chloride. It is typically only the reactant side because in all these, the solids are always on the left and they're not included in the equilibrium expression. So what this allows us to do, for example, if we take something like silver chloride and we want to know, for example, how much we can dissolve in water or figure out how much we can actually get to dissolve in water, we could actually do something like that, like this problem here. If we take that equilibrium and we write our KSP, which is equal to our silver concentration times our chloride concentration, and that equals 1.6 times 10 to the minus 10. We could actually do our ice table here. And in this particular case, we're not going to even worry about the reactants. And the reason we're not going to worry about the reactants is it's a solid. So it will have nothing to do with the equilibrium. So we're just going to leave it blank. We're going to start with zeros here. This would then be normally minus x, but we're not going to worry about it. This would then be plus x, which means at equilibrium, x and x. This would go into our expression here. And this would give us basically x squared is equal to 1.6 times 10 to the minus 10. And as you can see here, you can take the square root of both sides. And that gives you an x of 1.3 times 10 to the minus 6. We'll borrow their number there. That is molarity. That is what is sometimes referred to as the molar solubility of silver chloride. That is how many moles per liter of silver chloride you could get to dissolve in 1 liter of solution, how many moles of it. That essentially is 1.3 times 10 to the minus 6 moles per liter. If I take the molar mass of silver chloride, which is 107.9 plus 35.45, gives me 143.35 grams per mole, and I multiply that by the molar solubility. That tells me that something like silver chloride, you could get approximately, and I think this is a typo, it's actually a 5 here. We'll fix it. I think it should be a 5. I think they do have a typo on this one here. And that tells you could actually get 0.002 grams per liter. That 0.002 grams per liter is how much silver chloride you could get to dissolve. So you could get 0.002 grams of silver chloride to dissolve in 1,000 milliliters of water or 1 liter of water, which is a lot of water and not a lot of solid dissolving. And that's why we think of something like this as silver chloride as being always insoluble, because even though it's mostly insoluble, it still can dissolve a little bit. And that's the thing that you just think about, especially if you go off to 1B. Sometimes we think of solubility rules as always 100%. That's always going to be the case. Whenever it happens, we will always get the solid if we put these two things together. There's actually, as you'll learn in 1B, a lot of factors like pH, like concentrations, and like other ions that are floating around that affect whether or not you actually will see the solid form and solubility. But again, something like this, as you can see from the calculation, you basically get none of it to dissolve, but a very, very small amount. And that's why it's considered to be insoluble. But still can dissolve a little. So everything has the ability, even though if it's insoluble, to basically dissolve a little bit. Any questions on that there?